Hello students, welcome to the VTU EduSat program on automata theory and computability. So let us continue with the second module, which is on regular grammars. So for any of the queries, so you can reach to my mail ID which is displayed. So today, we will be discussing about first regular grammars. Okay. So in the module 1 we have seen the FSM construction, that is the finite state machine construction, and in the module 2 we have seen the regular expression. There is one more way of defining the regular language, that is through regular grammars. Next we will see some examples of regular grammars. Next, how they are equivalent. So like regular grammars and regular languages. Next we will see the algorithm for grammar to FSM. So that is here for the given grammar, how to convert into the equivalent FSM. So there exists an equivalent finite state machine for the grammar. So next we will see some of the examples of grammar to FSM. So next we will see the algorithm, so which is FSM to the grammar. So like how we have converted from the grammar to FSM. So here we will be seeing the finite state machine to how to convert it to grammar, and we will work some of the examples. And lastly, so how this regular expression, regular grammar and finite state machine can be given for a given language, and if there are two languages, how the grammars will satisfy the multiple criteria. So let us start with regular grammars. So regular grammars, they are also called as right linear grammars. So a regular grammar, it is a quadruple which is defined with 4 tuples, that is V, sigma, R and S. So what is V? Here V is the rule alphabet which contains non-terminals and terminals. So non-terminals, these are usually denoted with capital letters and they are used in the derivations. To derive any string, okay, so we will start with the non-terminal, that is the start non-terminal, and sigma, as we have seen, it is an input alphabet. Here it contains the set of terminals and it is a subset of V. Okay. So V contains all non-terminals and terminals, whereas sigma, it contains only the set of terminals. So for example, so while working in the module 1, so we have seen sigma consisting of A and B or 0 and 1. So similarly here, if you have a string ABB for example, so it should be contained in the sigma. Next R, it is the set of rules, and here we will define some rules, and it is a finite set of rules of the form x derives y. So there are some criteria to define these rules, we will see next. And S is the non-terminal, and it is a start symbol. Okay. So for grammar to be defined, it is defined with a quadruple V, sigma, R and S. V contains, it is a rule alphabet which contains non-terminals and terminals, and sigma, it is a set of terminals. So that is all the strings will be derived from sigma, and R, it is the set of rules, and S is the start symbol. So how a rule should be? So all rules in the R should be left hand side, it should be a single non-terminal, and right hand side either it can be epsilon or a single terminal or a single terminal followed by a non-terminal. For example, if we consider these 3 rules, so these are legal rules. So here S derives A is there, that means so S derives a single terminal which is allowed, and here if you consider S derives epsilon is there. So epsilon it can be contained in the rule, and here next if you consider T derives a single terminal followed by non-terminal. This is the only these three type are allowed in the rules, and these are not legal rules. So, for example, so if you have an like rule like S derives ASA, so this is not allowed, because only AS it can have, afterwards again it cannot have the terminal. And here S derives TT, that means two non-terminals are not allowed on the right hand side. And similarly here ASA, okay. So, always left hand side it should be a single non-terminal, like this you cannot have, and also you cannot have a single non-terminal deriving a non-terminal. So, always a non-terminal derives a terminal or terminal followed by non-terminals. So, while defining the rules, okay, so for any grammar if you are writing the rules, so you should keep this in mind and then you should write the grammar. So, the language generated by the grammar. So, like by the grammar, any grammar V, sigma, R and S, it is denoted by L of G. What does L of G contains? It contains a set of all strings of W in sigma star, such that it is possible to start with S, and you can apply some finite set of rules in R and derive W. So, that is the derivation process. How do you derive the string? So, you should start with the start symbol and then so go on applying the rules. So, by seeing which string you are deriving, and start symbol of any grammar will be the symbol on the left hand side of the first rule in the RG. Okay. So, RG contains the set of rules. So, let us see one example of regular grammar. Let us consider the example, so where even length strings. Okay. So, let L equals W, which belongs to AB star, such that mod of W, that is length of the string W, is even, and we know how to write the regular expression. Okay. So, what will be the regular expression? It is either A union B followed by A union B whole star, or it can also be written as AA union AB union BA union BA whole star. Okay. So, and if you write the DFSM which accepting this L, so it can be written, it can be designed with two states S and T, okay, such that S on A or B it reaches T, and T on reach and on having a transition with A and B it reaches the final state. So, the regular grammar which defining the L. Okay. So, now so you should write the grammar which defines L. Okay. So, we know that any grammar which is defined with 4 tuples. So, first it contains some set of non-terminals and terminals, and also it contains sigma. Here obviously sigma is A and B, because all strings are derived from this alphabet, and so the rule alphabet, it consists of capital S, T, these two, and also the terminals A and B. Okay. So, now S is a start symbol, and then so you should write the rules also. So, these are the legal rules which derives the string. For example, so S derives epsilon is there, S derives AT, small a followed with capital T, and S derives BT. Why starting with S you have 3 productions? Okay. So, because Y is here, S is also a final state, hence it can be epsilon. You can derive the string epsilon, and here starting from S you can have the strings either A or B. Okay. So, that is why it should have the string starting with A and B. So, that is why S derives AT and S derives BT is included. Okay. So, next afterwards, so it can be anything. So, that means T can be, it can have either A or B. So, that is why we have written T derives AS and T derives BS. So, let us derive the string using some rules. So these are the rules of the previous problem, that is to accept the even length string. So let us derive the string AB, AB. So if you consider here AB, AB, it contains the string is AB, AB, which contains the symbols A and B, and it is of even length. Okay. So we will start with S. We have the rule S defined, S derives AT. So first we will apply that rule, S derives AT. Next A write as it is, and we have a rule T derives BT. Okay. So T derives BT. So that rule we have applied it. Next next AB, and then T derives AS, T derives AS. Next ABA will keep it as it is, and then S derives BS. Okay. So finally S derives epsilon is applied, and we have the string AB, AB. So like this, so you can derive any strings using these rules of even length. Okay. So you should write a grammar in such a way that it should not generate the strings of odd length. Okay. So however you apply these rules, so it should generate strings of even length only, then your grammar will be correct. Now, so let us see the equivalence of regular grammars and regular languages. Okay. So regular grammars define exactly the regular languages. So in the module 1, so we have seen the finite state machines to define the regular languages, and in the module 2 we have seen regular expressions are another way of representing the regular languages. And here also similarly, so you can represent the regular languages by using regular grammars. So like Kleen's theorem, how we have proved for every FSM there exists a regular expression, and for every regular expression there exists an FSM. So here also, so you can prove that the class of languages that can be defined with regular languages is exactly the regular languages. So that is, so the proof is, so you need to show from the regular grammar you can construct an FSM, and from the FSM you can construct a regular grammar. So next further, so we will see the theorem and the algorithm of converting this and some examples. So this is the algorithm which constructs an FSM. So all here proofs, so we will do it by construction. Okay. So this algorithm, it constructs an FSM from a regular grammar G equals V sigma R and S, and assures that L of M is equal to L of G. That means the language accepted by the finite state machine is exactly, it should be equal to the language which is accepted by the grammar. So what does it mean? That means, so when you derive the strings by applying the rules of this grammar, so you will get the strings. Okay. So similarly, that strings, if you are traversing through the finite state machine, it should reach the final state. Okay. So then you can define that both the languages are same. So let us see the algorithm of converting the grammar to finite state machine. Okay. So here the input is the regular grammar. So what is the first step is, we will create in M a separate state for each non-terminal in V. Okay. So grammar means it will be having the rules. So by seeing the rules, we will come to know how many non-terminals are there. So if there are 3 non-terminals, then create 3 separate states. Next, make the state corresponding to S the start state. Okay. So the start variable or the start variable which non-terminal will be using, so that will become the start state. And if there are any rules of the form X derives W for some W which belongs to sigma, okay, then create an additional state labeled hash. Okay. So for each rule of the form X derives Wy, so we create a transition from X to Y labeled W. Okay. So, and here if any non-terminal, it derives only the terminal, then we will add an extra accepted state as hash. Okay. So, keeping these steps in mind, we can convert, and then we will add a transition from x to y labeled epsilon, and for each rule of the form x derives W, add the transition from x to hash labeled W. Okay. So, that is the third one whatever we have defined. So, that is again redefined here. So, we will create another state with accepted state hash, and then for that we will write we will add the transition W. Okay. So, these 5 rules using we can convert the grammar to FSM, and last one is for each rule of the form x derives epsilon, mark the state x as accepting. That means, if any of the non-terminal is deriving epsilon, then you can mark that state as accepting. And if you want to construct an DFSM, okay, so there will be some dead states. Suppose if M is incomplete, then so you can add the new state D, and then you can define the transitions. Okay. So, for every I in sigma, create a transition from D to a D labeled I. Okay. So, this is in case if you require a DFSM, or simply FSM means, so each rule you can convert into the FSM. So, let us see how to construct from the grammar to FSM by taking an example. Okay. So, I have considered here the strings that end with A. Okay. So, sigma is defined over A and B. So, strings W, it consists of the strings of A and B, but W end with the pattern A. At the end 4 A should be there. So, starting it can have either A or B. So, if you consider the grammar for this, or if you construct the regular grammar, so starting if you see either it can have A or B, and it can be repeated any number of times. So, that is why S derives AS and S derives BS is there. So, here union is there either A or B. So, that is why both you can write the rule like this, S derives AS and S derives BS. Okay. After once how many A's or B's it has been derived, you want 4 A's compulsory, because so your language is defined like that. Okay. That is, it should be containing the pattern A. So, that is why here afterwards S derives AB, next B derives AC, C derives AD, and D derives A. So, if you observe here, we are deriving 4 A's, because the given language, so it contains at the end 4 A's compulsory. So, if you want to convert into the given grammar to finite state machine, how to construct it? So, as I said you, as a rule 1, how many non-terminals are there? So, you take those many states. So, if you observe here S is there, yes, next B is there, so B, next C is there, C as one state, and then D as another state. Okay. So, initially we will take these 4 states. Next S is the start non-terminal, that is the start variable. So, here S becomes the start state. So, you have S derives AS. So, again, so with A, and then you can define a self loop like this, A, S, and you have S derives BS. Okay. So, S derives BS. So, I have added here B also. Next, what is the rule? S derives AB. Okay. So, that means S derives with A, it makes a transition to state B. Next, B makes a transition to state C with the label A. Okay. So, that is B to C you can write as A, and similarly C to D as A. So, lastly D derives a single terminal. So you can take one accepted state hash, and then you can make this as a accepting state, and you can write here the transition A. So this is the equivalent FSM for the language that end with the pattern AAA. Next, let us consider the missing letter language. So in the module 1, so we have seen the missing letter language. So throughout the book, the author has considered the same examples. Okay, so that's why, so I'll be considering the same example. So what is that missing letter language is L missing. We can define with L missing. So it consists of a strings of W such that there is a symbol A which belongs to sigma not appearing in W. That means, so out of these three, any single symbol is missing, it should reach the final state. Okay. So the grammar G for generating L missing is these many productions are there. So this is the grammar. So now using this grammar, so you should construct the FSM. So how to construct the finite state machine? So first, if you observe, again I have rewritten those rules. So here how many non-terminals are there? S, B, C. Okay. So A, B, C. So those many states we have drawn it. Next you have S derives epsilon. So you can make this as accepting state. Next S derives AB, AC. So likewise S derives you have BA, BC. For all that previously algorithm was defined, no? In the same way you write the transitions. We will write the transitions, and here if you observe A derives epsilon is there. So we can make A also as accepting state, and B derives epsilon is there. So you can make B also accepting state, and C derives epsilon is there. So you can make the accepting state. So for each rule, so you can write the transitions. So as previously described. So this is the FSM for the missing letter language. Now, so let us concentrate on some more examples, so which we have discussed in the module 1. So we know how to write the strings that start with ABB. That means your language consists of a strings of A and B, in that starting with ABB. Okay. So if you write the regular expression, it will be ABB followed by A union B whole star. Okay. So if you write the grammar will be like this. So that means starting, you observe here ABB is compulsory. Afterwards it can have either A or B, and it can be repeated 0 or more number of times. So if you want to write the grammar for this, so first it should generate small a only, because it should not generate here B. The language, it consists of first starting with ABB. Okay. So first S generates AB, next B generates BC, next C generates BT. Okay. So once ABB it has been generated, next T can have either A or B or epsilon. So the grammar if you write, so it will be having these rules. Using these rules, so you can construct the FSM. Okay. So here as you observe S, B, C, T, 4 states you can write it, and then so you can write from S derives AB is there. So you can make a transition from S to B with A. Next B derives small b capital C. So from B to C you can connect with the transition B. Next from C to T you can connect with B, and then T derives A and B. So you can write the self loop, and lastly T derives epsilon is there. So you can make an acceptance state, and then you can make it as a accepted state. Now, so we have written the starting with ABB. Let us see how to write the grammar and the FSM for ending with ABB. Okay. So, here the regular expression will be A union B whole star and ending with A and B. Okay. So, if you consider the grammar, so we know the FSM will be like this. So, S T B hash, and if you want to write the grammar, S can derive either AS or BS, because if you observe here the strings are A union B whole star. Next, S can derive either A, okay, followed by T. Why? Because here ABB is compulsory. Next, T derives BB and B derives B. So, the same thing, equivalent FSM, if you write it, so it will be like this. So, for starting, S derives AS or BS, next S derives AT, next T derives BB, next B derives small b is there. So, we will make this as acceptance state. Next, let us write the grammar that contain the substring 001. So, if you observe here, so here the L is the language which consists of W which belongs to 0 and 1 instead of A and B. So, I have taken 0 and 1, strings of 0 and 1 with 001 as the substring. So, if you write the regular expression, so it will be 0 union 1 whole star followed with 001 followed by 0 union 1 whole star. So, before and after this 001, so you can have any strings of 0 and 1. Okay. So, if you consider the FSM, so FSM will be like this, and if you write the grammar, so the grammar will be like this. So, starting S derives 0 or 1 is there. So, S can derive either 0S or 1S. So, next followed with 0T, next T followed with 0P and P followed with 1X. Why this is compulsory is because you need to generate 001. Next, afterwards X can generate either 0 or 1 or epsilon. Okay. So, this can be, the FSM can be like this. So, that is S generates 0S or 1S, next S derives 0T, next T derives 0, sorry it is P, and then P derives X. Okay. So, and X derives 0 or 1 and even it derives epsilon. So, you can make this as a final state and then you can construct. Next, let us see the algorithm of converting the finite state machine to the grammar. Actually, this is an exercise given in the textbook. Only the grammar to FSM is given, but FSM to grammar it is not given. Okay. So, first step is make M deterministic. If you are not making M as deterministic, that is deterministic finite state machine, it is also okay, but there should not be a epsilon transitions. Okay. So, if you want to eliminate the epsilon transitions, only one way is, so you can convert into the equivalent DFSM. If epsilon transitions are not there, then with FSM only you can continue. So, how to proceed? Create a non-terminal for each state in the new M. So, the reverse way, so for each non-terminal we have created a state, and here for each state we will create a non-terminal, and so start state becomes the starting non-terminal, that is a starting non-terminal. So, it will become the grammar starting rule. Okay. And for each transition delta of T comma A equals U, make a rule of the form T derives AU. Okay. And for each accepting state make a rule of the form T derives epsilon. Okay. So, let us see the example of building the grammar from FSM. Okay. So, this is the grammar. So, A derives AB and A derives BD. Sorry, here we will consider the finite state machine. So, it is having how many states? 4 states are there, A, B, C and then D. Okay. So, we will write 4 non-terminals, and here A is the start state. So, A will be the start variable of the or starting non-terminal of the grammar. If you observe here, A derives A and then B. That means A is making a transition of A and it is traversing to B. So, you can make a rule as A derives AB, and if you observe here, A derives BD is there. So, A derives BD. Next, B derives BB, that is, it is having a self loop. So, you can write small b followed by non-terminal B. Next, B derives AC. Okay. So, that is, so it is making a transition to state C with A. So, you can write B derives AC. Next, D is making a transition to state B with B, okay, with small b. So, we can write D derives BB, and here since C is the accepting state, so you can always write C derives epsilon. Okay. So, this is the example we have discussed in the regular expression, and if you want to write the regular expression, so regular expression will be either BB, A union BB followed by B star A. So, this will be the regular expression. Next, A union BB B star A. So, the same thing, A derives building grammar from the FSM. Okay. So, now we will derive the string. Okay. So, we know this was the previous regular expression. So, you take any string which belongs to this regular expression. So, here I have taken ABA, here A followed with B A. So, you can derive this string using the rules of the grammar. Okay. So, first you can apply A derives AB. Why I have to apply AB only? Because my string contains ABA. So, you should apply this rule only. So, even though it has BD, I should take AB only because the string I wanted is ABA. Next, B derives BB. So, this rule I have applied. Next, B derives AC. So, this rule I have applied. So, lastly, I have applied C derives epsilon. So, you can derive the string using these rules. And similarly, so I have derived the string BBA. So, this is starting with A and this is starting with B. So, starting with A means, so it here actually it can contain either A or BB. So, here I have taken a string BB followed with A. Since here star is there, so it can be 0 or more number of times. So, let us derive BBA. So, you can start with A derives BB, A derives BB, next B derives BB, next B derives AC, and lastly C derives epsilon. So, like this, so you can derive the strings from the grammar. So, let us consider the example of a simple FSM with no simple RE. So, while discussing the regular expression, we have constructed a very complicated regular expression for this. So, what was the problem? The problem was defined on a language which contains an even number of A's and an odd number of B's. Okay. So, if you consider the FSM, so the FSM will be of this type. So, which contains 4 states, and we have made C as the accepting state. So, this will be the grammar. Okay. So, an FSM with no simple RE, how to convert it? So, if you observe here, there are 4 states A, B, C, D. Okay. So, you can take A, B, C, D as the non-terminals, and A, you can start with A derives AB, A derives BC. So, like that you can define all the transitions to the rules as previously have explained. So, like that you can define. Okay. So, this is the grammar, and So let us see how to derive the strings. So using this grammar, you can derive I have taken ABA, BB. So if you observe here, A is of even length and B is of odd length. Okay. So likewise, so you can apply these rules. So how we have got these rules is from the previous FSM. So you can convert into the grammar. So grammar means writing rules. Okay. So FSM means you should define the transition. Grammar means you should define the rules. So using those rules, so you can derive the string. Let us take an example of regular expression, regular grammar and finite state machine for a given language. So what is that is L consists of a language, consists of a strings W which belongs to AB star, and every A in W is immediately followed by at least one B. So that means here if it has an A, it should be followed by B. So your language can consist of only one B or AB or AB AB. If A is there means it should be followed by B. Okay. So at least one B. So if you write the regular expression, so regular expression will be AB union B whole star. It can be single B, 2B, any B's, but if A is there means A should be followed by B. And if you write the grammar for this, so you can generate either, if you are generating A, then you should generate B, or else so you can generate B. Okay. So I can write as S derives AT and S derives BS and S derives epsilon and then T derives BS. Okay. So if you construct the FSM, it will be like this with two states S and T. Okay. Starting with S, so S derives AT, next T derives BS, next S derives BS, and also S derives epsilon is there. So you can make this as the final state. Now, so let us see the language which satisfies the multiple criteria. That means here let us consider the strings W, and W contain an odd number of A's and W ends in A. Okay. So here he has specified the two conditions. W contain an odd number of A's and W ends in A. Okay. So that means all the strings should end with A and it should contain the odd number of A's. Okay. So if you write the FSM, so FSM will be like this. So that is starting with S, A, T, then afterwards it can be anything. Next, so here with one more A, so it reaches the state S. Okay. So similarly, so if you write the grammar, equivalent grammar will be like this, odd number of A's. So this is first I have generated an odd number of A's. So next it should end with A. And generating the string BAA, BA. So this is one example I have derived. Okay. So if you observe here string, it contains odd number of A's and this string end with A. Okay. So either you can write the FSM, from the FSM you can write the grammar, or you can write the grammar and then you can construct the FSM. But normally, so what we do is, so while writing any language, first thing is we write either the FSM or the regular expression, because they are easy way and they are standard. So you cannot write the grammar very easily like FSM. So FSMs normally will use it finite state machines, whether it is DFSM or NFSM, so you can write it. But writing this grammar is of it is of not so easy. So either we will write the regular expression or the FSM, and then so you can convert into equivalent grammar. For simple languages, so you can generate the grammar. So if it is like satisfying like this multiple criteria, so then so it needs some experience or you should have worked with more examples. So, my suggestion is first write the regular expression or the FSM. From the FSM, so you can write the grammar. So, let us see conclusion on regular grammars. Okay. So, regular grammars, as we have seen, they define exactly the regular languages. They define exactly the regular languages, but regular grammars are often used in practice as, so they are not so familiar. So, as I said you, it is easy to write the FSM or the regular expression, but it is not so easy when the languages are very complicated. So, you cannot write the grammar. So, they are very less often used in practice. And further, if we move further, so there is no concept of regular expressions also, because easily we will be moving to another type, that is the context free languages. Okay. So, context free languages, they are the languages which are designed to accept the push down automata. Push down automata, they are special kind of finite state machines with stack. Okay. So, here, so normally, so if the language is not regular, then so you can accept that language. Suppose for example, a power n, b power n, if you consider for n greater than 0, so it is not a regular language. Okay. So, you cannot design a finite state machine for this language, but you can design a push down automata and you can write the context free grammar, and the languages accepted by this push down automata will call them as context free languages. Hence, further, so we will be not discussing the regular grammars, we will be discussing the CFG and CFL, which are designed for push down automata. So, in this context, regular grammars are not so used in practice. They define exactly the regular languages, even then they are not used. So, let us summarize what we have discussed. So, first we have discussed on regular grammars. Next, we have seen the algorithm, so where we constructed the FSM from the given grammar. Next, we have considered the algorithm, that is the FSM to grammar. So, in both the ways, so if a grammar is given, you can convert into equivalent FSM, and if an FSM is there, so you can write the equivalent grammar. So, next we have seen all the three types, that is writing the regular expression, regular grammar and the finite state machine for the given language. So, if you have any queries, so you can reach me at this mail ID. Thank you, one and all.